Hi, this is Gordon Parker from Michigan Tech, and in this video we're going to explore first-order systems, and in particular DC gain, time constant, and whether or not we can throw away extra poles. We'll do this through analysis, but then also play around with it a bit in MATLAB and Simulink. So here's where we're going to start. Here's a transfer function, an output over an input, and it's very general in its form. It has some constant in the numerator and a pole at -a. So one thing we can do with this, as we play a little bit, is we can make a pole zero diagram. Of course, it's a rather boring one. We just have a single pole right there at -a. Let's assume that a is positive. So in everything we do here, we'll make that assumption. Well, let's play around with it some more. Let's go ahead and let the input be a unit step, 1 over s. So we could solve for y, which would now be k over s plus a. When we bring this u over to here. And now I could go ahead and solve it. I could do a partial fraction expansion, like so, and calculate what my C1 and C2 are. C1 is going to be, let's see, s times y, and then let s equal 0. So I'll get k over a. And then C2 is s plus a times y. Then we let s equal -a. And for that, I would get negative k over a. So I can write out the solution now. We have y of t is equal to k over a step, so that gives me a 1, minus this piece, which would be e to the -at. Beautiful. And what else can I do? I could sketch it. Why not? So here's a t, here's a y of t. Here is this final value that it goes to. I can see that it's going to be some final value because when I let y go to infinity here, I'll get k over a. 1 minus this term goes to 0. So I just get k over a. And the response looks something like this. Classic first order response. It doesn't really keep creeping up like that. It just goes up to that dashed line and stays there. Oh, hey, so since we looked at the final value here, y equal infinity, let's go ahead and use the final value theorem. See if we get the same thing. So for the final value theorem, I would go, the limit as s goes to 0 of s times y of s. And so that's the limit as s goes to 0 of k over s plus a with an s due to that s. They cancel out, and so I get k over a. Well, that checks. Checks exactly with what we postulated or the conclusion we came to from looking at y of t. We could also do the DC gain. Right? The DC gain is defined as hitting some system with a unit step input and then looking at what the final value of that response is. And what that tells us is that if we were to excite that system with a unit step of any other magnitude, then we can take that DC gain, multiply it by that any other magnitude, and that will be the value of the response as time goes to infinity. And we have a canned way of doing that, or calculating it. We can take the limit as s goes to 0 of g of s. And so that is the limit as s goes to 0 of k over s plus a. And so again, it's k over a. Great, so our DC gain is k over a. Our final value was k over a. That's very consistent. Well, now let's look at this first order system in a slightly different form. So I'm going to rewrite this as, I'll have the k in the numerator, but I'll factor out the a from the denominator. So I get that. And then what I'll do is I'll say what we have in the numerator is the DC gain, k over a. In the denominator, we have this, tau s plus 1, where tau is defined as 1 over a. And we call that the time constant. And it has units of seconds. Another parenthesis there. Well, now let's try to relate y of t to our time constant. And the way we'll do it is we'll simply, since we know that the time constant is some time in t, we'll just go ahead and evaluate y at tau. So this was our y of t, and I'm going to replace t with tau. So I get e to the negative a tau. But of course tau is 1 over a. So what I really get is k over a, 1 minus e to the negative 1. Well, that's interesting. This is just a constant. 1 minus e to the negative 1 is about 0.63. So y of tau is approximately equal to 0.63 times k over a. That's a huge result, because what that tells us is that if I hit a first order system with a step input, and then I see that classic first order response where it's going like this, when I find the point where that step response has arrived at 63% of the final value, the corresponding time, that time is tau. So now I can get k over a from the final value, my numerator of my transfer function, and I can get tau, basically the pole location of that first order system. It's a wonderful result. Now, let's do one more thing before we jump into MATLAB. Let's say that I have a new transfer function, a different transfer function of some system that looks like this. It has 2 real poles. It could have more than 2, but let's just do the 2 case first. Let me draw a pole zero diagram of this thing. Let's say that A1 is here and A2 is down here. So of course that distance is A1. That distance from the imaginary axis is A2. Here's the interesting part. If that distance, I'll use absolute value, A2, is much, much greater than that distance, A1, then A2, or I should say, maybe I should say it as the pole, I'll write it like this, S plus A2, that whole term can be neglected. We can toss it out. So if that was the case, that means that my G1 is approximately equal to, well, you might be tempted to say this, right? I've tossed out this S plus A2 term. That's actually not correct. The reason it's not correct is that you have to match DC gains of the original system, that is this system, and your approximate system. So the DC gain here is k over A1, A2. So when we do this tossing out of S plus A2, we have to make sure that we maintain that. So I can put my piece of that, the contribution of S plus A2 to the DC gain in the numerator and go like so. That's good. Its DC gain is again k over A1, A2, which matches this one. And I've tossed out that pole that's far away from A1 in the left half plane. Now you might say, well, how far does far have to be? It depends on how accurately you want your approximate system to match the original system. So it depends on what your needs are. But a conservative rule of thumb would be to say that if A2, that distance, is greater than or equal to 10 times the A1 distance, then you can neglect it. And again, this is for just one other pole, but if you had several other poles. So let's say you had an A1 here, and you had an A2 and an A3, and these were all far away from the imaginary axis compared to A1, then you could get rid of all of them. Okay, so with all that background, let's go ahead and explore some of these topics in MATLAB and Simulink. Okay, so here we are with MATLAB, and what I'll do is I'll load up some data of a step response of a first order system. And it's appropriately called My Data. Because it wasn't mydata.dat, it was a mat file. There we go. And it has three columns. The first column is time, and the other two columns are the step input and the measured response. So let's take a look at this. My data. So here we'll get the input onto the grid. And with this, we'll get the step response onto the grid. Speaking of grids, let's go ahead and put a grid on it. Okay. Whoops, that's not what I wanted to do. There we go. I'll just stretch it out a wee bit like so. Great. So what do we have here? The system was given a step input at time equal 1 second, and that step input had amplitude 2. And then here is the response in green, has some noise on it. And what we'll try to do is obtain the transfer function by looking at this data. Well, the first thing we can do is get the DC gain. That would be this amplitude, 7, divided by the amplitude of the input, which was 2 in this case. So I'll just keep track of that here. DC gain is 7 divided by 2, or 3.5. Now what we need to do is put a cursor on here and find the point where the step response gets to 63% of the final value. So the final value was 7 times 0.63, and so I have 4.41 as that point that I'm looking for. Now what I have here is the x and y, so this is 2.27 seconds and 6.823 in the y-axis. So I'll just scoot this down until the y gets to 4.41. We're close to it. How about, well, I'm kind of picking at nits here. That's looks like about as close as I'm going to get. So can I get any closer than that? Not really. So 1.39, 1.4, somewhere in there is the time that we're looking for. Now that's actually 1.39. Let's use 1.4 just because that's a nice rounder number. So we'll call that 1.4. But really the step input started at time equal 1. So the time from where it started to where it ended up at 63% was only 0.4 seconds. So our tau, our time constant, is 0.4 seconds. So let's go ahead and form our transfer function using the TF command. In the numerator we'll have the DC gain, and in the denominator we'll have tau times s, which is implied in that statement, plus 1. So there it is. Now we can go ahead and check it. And the way I'll check it is I'll generate a step response using the step command and then overlay it onto the plot that we just had. So let's create a time vector. I'll just go from 0 to 5 seconds, maybe by 0.01. And we'll go ahead and create our step response using that time vector. Great, so now I have a t and a y, but MATLAB step response does a couple things that aren't quite what we need. Let's look at it first, just so we can see that. So I'll throw this on, hold on. Now everything I do for plotting will just be laid onto the figure that I have open. So I'll go plot ty and we'll make it black. So a couple things. It started at time equals 0, so I need to shift time by 1 second, no problem. But also MATLAB uses a unit step input, not a step of amplitude 2. So I can get around that by just taking the output and multiplying it by 2. I don't have to actually convince MATLAB to use a step of amplitude 2. I can do it on the output side. So now we'll go plot t plus 1 to get that shift in time, 2 times y, and we'll use red, how about, and we'll make it a nice thick line, 2. And look at that. That's a beautiful thing, right? We were able to estimate the transfer function from this data, and it's a very good fit. So now we know that the system we're dealing with, simply by looking at this step response, is this one. And we could then go forward, design a control system for it, or do other types of analyses. Well, that was good. Now let's explore that notion of throwing out poles that are far away from a dominant pole that's close to the imaginary axis in a relative sense. So I'll start with a fresh block or a fresh model window and go over here to continuous and grab a transfer function. And that's as good as any. I'll now grab a source, which is a step, just so we can see the effect of the step on the step response of throwing out higher or poles that are far away from this one in the left half plane. So now what I'll do is I'll grab this one, right click on it and drag it. That makes a copy. And I'll take this one and give it a much slower time constant, or I'm sorry, much faster time constant, 0.1. So this one has a time constant of 0.1 seconds. This one has a time constant of 1 second. This one is close to the imaginary axis compared to this one. This one is far away from it, 10 times farther away in the left half plane. And so now we'll grab from the sinks, we'll grab a scope. Oops, that's not sinks. There we go. And what I'm doing by cascading these two together is it's a shortcut manner or a lazy way of creating a single second order transfer function with those two poles. And what I mean by that is I could have done this where I use the convolution command and I'll give it 1, 1 as one pole and then 0.11 as another. And now this system is identical to these two. I'll keep that around just for fun, just to illustrate that they are identical. And go into signal routing, grab a mux block, hook all these up. There we go. And let's go into the configuration parameters. 10 seconds, that's fine. Fixed step, that's fine. Third order, we'll simulate at 100 hertz. 100 hertz is way fast enough to capture all the dynamics associated with this system. So now we can just run it. Ding. So here we have the step response, and there's a yellow line and a pink line, but the yellow line is buried underneath this one, but they're identical. Okay, so we haven't done any simplifying yet. We're just looking at the original second order system. But now let's go ahead and grab this one, bring it down here, do that. I'll expand this mux block 1, bring this into here. So now what I'm doing is I'm throwing out this fast extra pole, the one that's far out in the left half plane. And now what we should see is a pink line and a yellow line, but we won't see the yellow line, we'll just see the pink, and then a blue line from that one. And lo and behold, that blue line is pretty close to our pink line. So this is the approximate system in blue, and the pink is the original one. Now, if I go in here and I put this pole even farther out in the left half plane, 0.05, and rerun it, now we will see the yellow line because that's sort of our original system. So it's a little noisy in that respect. So we have the blue line here, which is the approximate one, and the yellow line, which is this one. And what we're seeing is that the yellow and the blue are getting closer and closer together as this pole gets farther and farther out in the left half plane. Now let's do one other thing. I'm going to actually get rid of this system because it's just adding unnecessary complexity to what we're really trying to understand here. So now we'll do that. Rerun this one. So now we're just back to our true system up here in yellow and the approximate system here in pink. Now what I'll do is I'll make this one close to that pole that we started with. So how about 0.5 second time constant? It's now only 2 times farther away from the imaginary axis than this one is. And now we get a response that's very different. Here's our original system in yellow, and here's our approximate system in pink. That's a pretty poor approximation. Probably wouldn't want to use that. So a factor of 10 is a pretty good one. Okay, so just to summarize, what we did is we played around with first order systems, introduced time constants and DC gain, and then looked at how we can simplify those first order systems by throwing out poles that are far out in the left half plane compared to the dominant one. Then we just played around with that in MATLAB and Simulink. Took some data and extracted a transfer function from it, and then showed how to use Simulink to explore that notion of throwing away extra poles. So again, my name is Gordon Parker from Michigan Tech, and thanks for watching.